Let's explore entropy, one of the most fundamental concepts in physics and information theory. Entropy is a measure of disorder or randomness in a system, and it has profound implications for understanding the universe. Let's start by understanding what entropy actually means. Entropy fundamentally measures the number of possible microscopic arrangements that a system can have. When entropy is high, there are many possible arrangements, meaning more disorder and randomness. On the left, we see low entropy with particles arranged in order. On the right, high entropy shows particles randomly distributed. Now let's look at how entropy is mathematically defined. The Boltzmann equation defines entropy as S equals Kb times the natural logarithm of W. Here, S is entropy, Kb is the Boltzmann constant, and W represents the number of possible microstates. The Boltzmann constant has a value of 1.38 times 10 to the negative 23 joules per Kelvin. With one particle in a box, there's only one possible state. With more freedom, the number of microstates increases dramatically. Entropy is central to the second law of thermodynamics. The second law states that in any isolated system, entropy can only stay the same or increase, never decrease. Mathematically, the change in entropy must be greater than or equal to 0. As time moves forward, entropy naturally increases, making the universe more disordered over time. This is why we see ice melt into water, but never see a glass of water spontaneously freeze without removing heat. Let's see how entropy manifests in everyday situations. A clean, organized room has low entropy with few arrangements. A messy room has high entropy with countless possible arrangements. When you add milk to coffee, they naturally mix. The mixed state has higher entropy than separated milk and coffee. Coffee and milk start separated, then naturally mix into a uniform state. This process increases entropy and cannot reverse spontaneously. Entropy also appears in information theory with a different but related meaning. In information theory, entropy measures the uncertainty or unpredictability in a message or data stream. Shannon entropy is defined as H equals negative sum of pi times log base 2 of pi. A repetitive message has low information entropy and is predictable. A random message has high entropy and maximum unpredictability. Let's understand the deep reason why entropy naturally increases. The fundamental reason is statistical. There are vastly more disordered arrangements than ordered ones in any system. One ordered state at the top. Several partially ordered states in the middle. Millions of disordered states at the bottom. Probability is proportional to the number of available states, so disorder is overwhelmingly more likely. Let's recap the key concepts about entropy. Entropy is a measure of disorder that counts the number of possible microscopic arrangements in a system. The second law of thermodynamics tells us that entropy can only increase or stay constant in isolated systems. Entropy explains why many natural processes are irreversible, like mixing, heat flow, and why time has a direction. The concept of entropy beautifully connects physics, information theory, and probability into a unified framework. Entropy gives time its arrow, pointing always toward increasing disorder and the eventual heat death of the universe.